Hello, I'm Yap Pui Wing. I will talk about Chapter 22, which is about the reaction of nucleophilic acid substitution involving the carboxylic acid derivatives. This is the content of my presentation. In introduction, there will be 3 sections. General structure of carboxylic acid derivatives, RCOZ. It has a R group bonded to the CO, naming an acyl group. The electronegative atom Z is a leaving group, so the nucleophilic acyl substitution can occur. By substituting the Z with different groups, we can get different derivatives. OH carboxylic acid, chloride acid chloride, OCOR anhydride, OR ester, NR square amide. If it is NH square, then it is a primary amide. NHR for secondary amide, and NR square when the R is alkyl group, then it is a tertiary amide. We also have nitrile. It is sometimes considered as a carboxylic acid derivatives despite its different structure from the carboxylic acid derivatives. Nitrile does not have a carbonyl group, but it has a sinyl group. The sinyl carbon has the same oxidative state as the carbonyl carbon of carboxylic acid derivatives. And also, both nitrile and carboxylic acid derivatives have one carbon atom with 3 bonds to the electronegative atoms. Characterization, structure and bonding. The carbonyl carbon is sp2 hybridized and has a trigonal planar geometry, making it uncrowded. The electronegative oxygen atom polarizes the carbonyl group. This makes the carbonyl carbon electrophilic, and it is easily to be attacked by the nucleophiles. The sinyl carbon is sp hybridized and has a linear geometry with bond angle of 180 degrees. The nitrile contains an electrophilic carbon also. The carboxylic acid derivatives are containing an atom Z with a non-bonded electron pair, so there are 3 resonance structures can be drawn. The resonance structures stabilize the derivative by delocalizing the electron density. The basicity of Z determines the extent of contribution of the structure tree to the hybrid. The more basic the Z, the more it donates its electron pair and more resonance structure tree contributes to the hybrid. So in order to determine and compare the basicity of the leaving group Z, we look into pKa values of the conjugate acid HZ. When the acidity of HZ increases, the pKa decreases, and so the basicity of the leaving group decreases. We can see that the chloride ion is the weakest base, followed by carboxylic ion, then OH and OR. Amine is the strongest base. We can conclude that the more basic the leaving group, the more stable the derivatives. Hence, acid chlorides are the most unstable compounds, whereas the amides are the most stable compounds. And as just mentioned before that, the more basic the leaving group, the more resonance effect contributed. So when the basicity of Z increases, the stability of the derivatives increases due to the added resonance stabilization. Acid chlorides, ester, and ketone have the similar boiling and melting points but lower than that of primary amide. For solubility, compounds with less than or equals to 5 are soluble in water. Compounds with more than 5 carbons are insoluble in water. In IR spectra, these are the absorption bond and their respective frequencies. These two are from primary and secondary amide. This is for the sinyl group in nitrile. Factors affecting the shifting of frequency for CO absorption. When the carbonyl pi bond becomes more delocalized, the CO absorption shifts to lower absorption. Conjugation also. For cyclic carboxylic acid derivatives, smaller ring size shift the CO absorption to higher frequency. These are their frequency in proton and carbon-13 NMR absorption spectra. General reaction of nucleophilic acyl substitution. The nucleophile attacks on the electrophilic carbon and replaces the leaving group Z. Reaction mechanism. When electron pair from the CO double bond move to the oxygen atom, and this makes the carbon electrophilic. Then the nucleophile attacks the electrophilic carbon and forming a tetrahedral intermediate. When electron pair move from the oxygen and forming a CO double bond, the ZZ bond breaks and Z leaves. This is the final substitution product. You can see the nucleophile replaces the Z. Overview reactions. By using different nucleophiles, respective carboxylic acid derivatives can be formed. The more the leaving group ability, the higher the reactivity. Amines are the strongest base, so they are the weakest leaving group. Hence, the amides are the least reactive and stable compounds. Chloride ions are the weakest base, so they are the strongest leaving group. Hence, acid chlorides are the most reactive and unstable compounds. For acid chlorides, they can form anhydrides, carboxylic acids, ester, and amides. Anhydrides can be converted to carboxylic acids, esters, and amides. Carboxylic acids can form ester and amides. Carboxylic acid can also be converted to acid chlorides using thionyl chloride, but not from the nucleophilic acyl substitution. To convert it to anhydrides, dicarboxylic acids must be heated to high temperatures to convert them into cyclic anhydrides under dehydration reaction. Esters are hydrolyzed with water in the presence of either acid or base to form carboxylic acid or carboxylic anions respectively. Ester reacts with NH3, ammonia, and amines to form the amides. Amides hydrolyzes in acid or base to form carboxylic acids or carboxylic anion respectively. Nitriles can undergo hydrolysis, reduction, and reaction with the organometallic reagent. The first selected journal is Enzymatic Synthesis of Fern-ethyl Ester from Fern-ethyl Alcohol with Acyl Donors. The journal is about figuring out the optimal conditions to synthesize the Fern-ethyl ester in shorter reaction time and higher enzyme reusability for high conversion of Fern-ethyl acetate. Recall that in nucleophilic acyl substitution reaction, the nucleophile replaces the leaving group Z. So in the journal, they use different types of carboxylic acid derivatives. The Fern-ethyl alcohol acted as the nucleophile and the carboxylic acid derivatives acted as the acyl donor. The reaction also used enzyme to catalyze esterification or trans-esterification to synthesize the final product, Fern-ethyl acetate. Fern-ethyl ester are the flavored esters used in foods, cosmetic, drinks, perfumery, and pharmaceutical industry. Examples of Fern-ethyl esters are Fern-ethyl acetate, butyl acetate, geranyl acetate, and citronellyl acetate. Remember that the research is to synthesize Fern-ethyl acetate, so we focus on it. The common way to synthesize the Fern-ethyl acetate is the extraction from natural sources, the roses. However, there are drawbacks. Hence, new solutions towards simpler and cheaper are much more encouraged. Fern-ethyl acetate is synthesized from a nucleophilic acyl substitution reaction using alkyl ester acetate anhydride as the acyl donor and catalyzed by an immobilized lipase. Acetate anhydride, which is the carboxylic acid derivatives, acts as the acyl donor. It has a symmetrical anhydride structure and hence has strong electron withdrawing effect, making the carbonyl carbon to be more electrophilic. This is the attack of the nucleophile. It has two carbonyl groups, one form the Fern-ethyl acetate and one form the acetic acid. Novozyme 435 is a heat-tolerant immobilized lipase with maximum activity at a temperature range of 70 to 80 degrees Celsius. The catalysis follows the serine hydrolysis mechanism, which will be explained later. So, how to synthesize the Fern-ethyl ester? There are two reactions involved. Nucleophilic acyl substitution reaction of Fern-ethyl alcohol with acetic anhydride as the acyl donor. Second reaction is the esterification or trans-esterification by the enzyme. They use the molar ratio of Fern-ethyl alcohol to acetate anhydride 1:4. Solvent used is isooctane in the shaking water bath. Optimal reaction temperature of 40 degrees Celsius. Centrifuge with 15 grams per liter Novozyme 435 at 150 rpm for 30 minutes. They also found out that with different molar ratio, all the conversion of Fern-ethyl acetate were above 75%, and also increases concentration of acyl donor, increases the reaction rate and the conversion. This is the simpler way to understand the reaction step. Firstly, the interaction of serine residue with the carbonyl carbon atom of the alkyl ester. Then, a tetrahedral intermediate is formed. The unstable enol is liberated as byproduct and an acyl enzyme complex is formed. Because the enol is unstable, it undergoes tautomerization to form the ketoform, which is the Fern-ethyl acetate. The second example is the development and in vitro evaluation of stearic acid phosphotyrosine amide as new excipient for zeta potential changing self-emulsifying drug delivery systems. Phosphotyrosine can act as a substrate to intestinal alkali phosphatase. In this research, it was conjugated with stearoid chloride to create a molecule with amphiphilic properties which allowed for an implementation into SEDDS, the self-emulsifying drug delivery system. Basically, The zeta potential changing self-emulsifying drug delivery systems are made up of zeta potential changing and self-emulsifying drug delivery systems. With an increasing availability of macromolecular drugs such as biologics and gene therapeutics, the demand for efficient oral drug delivery systems is rising. However, there are few drawbacks in the oral delivery. So these zeta potential changing drug delivery systems is to overcome these challenges. The nanocarriers in this system are equipped with certain side chains that are substrate for membrane-bound intestinal enzymes. At first, the mucous layer is a negatively charged system. After the penetration, enzymatic cleavage of the side chain of nanocarriers induces a zeta potential change, and the system now becomes positively charged. The zeta potential change facilitates the immobilization of the nanocarriers on the epithelial surface, and also the cellular uptake is being promoted due to the increased residence time and a favored endocytotic uptake of positively charged particles. In self-emulsifying drug delivery systems (SEDDS), it is known that it has a good mucus permeability abilities, high cellular uptake, and able to protect the encapsulated drug load from enzymatic degradation. Hence, we can see that the combination of systems can help to overcome the problems. The stearic acid phosphotyrosine amide is synthesized through the nucleophilic acyl substitution reaction of amino group of phosphotyrosine with the acid chloride group of stearoyl chloride. This is the simpler way to understand the reactions step. Firstly, stearoyl chloride is heated to 60 degrees Celsius and mixed with N-methyl-2-pyrrolidone, which is a solvent. Then, phosphotyrosine is dissolved in the mixture and incubated for 90 hours. The reaction mixture is precipitated with water, then the product is purified from the solvent and washed several times with water. Then, to prepare the SEDDS, they set up formulations composed of stearic acid phosphotyrosine amide in 4 ratios and combinations. Each formulation was mixed and homogenized at 70 degrees Celsius. The objectives of the research are to investigate zeta potential change, investigate enzymatic cleavability of the stearic acid phosphotyrosine amide incorporated in SEDDS by cargo-2 cells monolayers, and also investigate diffusion of SEDDS formulations through mucus. To investigate zeta potential change, the SEDDS emulsions were mixed with intestinal alkaline phosphatase (IAP) and incubated at 37 degrees Celsius. Then they determined the zeta potential before and after the addition of IAP. To investigate the enzymatic cleavability, cargo-2 cells were grown in 24 well plates and incubated at 37 degrees Celsius with carbon dioxide for 14 days. Then, the emulsions were applied to the cells and incubated for 2 hours. Sulfuric acid was added to stop the enzymatic reaction. Malachite green assay was employed to quantify the amount of cleaved phosphate. To investigate the diffusion of formulation through mucus, first the mucus was scraped off the tissue of small intestine. Then it was purified and homogenized by mixing with sodium chloride solution and centrifuged at 4 degrees Celsius for 2 hours. The emulsions were incubated with and without IAP for 2 hours at 37 degrees Celsius under gentle shaking at 300 rpm to obtain samples with positive and negative zeta potential. Phosphatase inhibitor was added to the samples without IAP to maintain its negative zeta potential. This investigation took place in a transfer chamber and a rotating tube. The conclusion of the research are that the stearic acid phosphotyrosine amide has amphiphilic properties, so it can be implemented in SEDDS presenting phosphotyrosine on the outer surface. It is also a promising excipient for the preparation of zeta potential changing SEDDS because it shows good mucus diffusion properties before and good immobilization in the mucus after enzymatically induced zeta potential change. Now for the summary, we see this trend from left to right. The basicity of the leaving groups increases, the resonance stabilization increases due to the added resonance, hence the leaving group ability decreases and the reactivity as well. The frequency of CO adsorption in the IR spectrum decreases because the carbonyl bond becomes more delocalized and conjugation. More reactive acyl compounds can always be converted to less reactive acyl compounds. but the reverse is not usually true. We can see that acid chlorides, which are the most reactive compounds having the best leaving group, can form all the other carboxylic acid derivatives. And for the amide, which are the least reactive having the poorest leaving group, can only form carboxylic acid. These are the references I used to make up my presentation. Thank you.